And now we have a second poster Blitz session. So I would like to ask anyone who has submitted or sent one slide but did not talk this morning to please come and line up on this side of the room. And we'll have the same strategy as this morning, 1 minute per person.
All right, so the image to the upper left, there is actually a GIF movie that shows a line channel map of the horse head in Carbon Plus. Come and talk to me, and I'll show it to you on my laptop. It's a open released observation for those of you who want to see it. So my point here is just to point out to you that the cycle 5 call for proposal for SOFIA is now out. There's about 475 hours of time coming up and about $5 million worth of GI funding, which I think a lot of people are interested in. The proposal deadline is on July 1st. Observations start in February. If you have any questions, come and talk to me. For this community in particular, I will point out that Hawk Plus will provide us with far infrared polarimetry at very high spatial resolution. And the upgrade array is a very fast mapper of, for instance, Carbon Plus and Oxygen 1. So again, SOFIA proposals, please. And if you have any questions, let me know. Thanks.
I can't read the name. Madon? Nope, okay. Who is this? Santos? Oh, okay. All right.
So I'm here. So we studied a lot of people have talked about the interstellar filaments, or the filaments of the ISM in molecular clouds. We studied simulation data that was replicating the conditions under which they're observed, and the 0.1 parsec width is well known. So we studied the effect of resolution limitations and Gaussian beam smoothing on the observed widths, and we found that there was in the low resolution Gaussian beam smooth data, we found that the 0.1 parsec widths was well reproduced. But in the high resolution data, we found that the widths became significantly more narrow, and this was consistent across numerous time steps. And so we concluded, and there's more analysis, and you can talk to me at my poster, but in effect, we just concluded that the resolution and the beam smoothing is having a very substantial effect on this 0.1 parsec characteristic filament width that we're seeing. Thank you.
Hello everyone, my name is Jia-Wei from Taiwan. So we perform optical and infrared polarimetry to work these beautiful filamentary clouds IC5146 seen by Herschel. So use our observations. In this poster, we highlight our estimations using our data to obtain the magnetic strength using transdiscovery method, regions by regions. So we can obtain a map of magnetic strength as well as the mass to flux ratio. And the results shows that in this cloud, the cloud is changing from subcritical in the diffuse region to the supercritical in the dense regions. So for more analysis, please come to read my poster. Thank you.
Hi, everyone. I'm Ben Wu, a grad student at University of Florida, and I'm looking at the dense and cold gas in giant molecular clouds, specifically looking at whether or not collisions between GMCs can create these high mass surface density, gravitationally unstable regions that we expect massive stars and clusters to form. And so we do simulations of magnetized turbulent clouds, looking at different colliding clouds and non-colliding clouds. And some of the analysis is we want to see if there are observational diagnostics that we can tell these two scenarios apart from. So we perform some similar studies to the Planck and Soler et al. Analysis of magnetic field direction with filamentary structures. We also have PDR models in the code, so we can try to reproduce integrated intensity maps, different CO rotational levels and C+. And so if any of this is interesting to you, please come see my poster. Thank you.
To study the star formation problem, the theory we need is not to be restricted by the strong or weak field condition, but to be generally applicable to both magnetized and turbulent molecular clouds in reality. Motivated by recent observations, we applied MHD turbulence in partially ionized gas, this theory, and investigate why are filaments ubiquitous. Why do filaments share a roughly constant width regardless of their density? How do filaments and cores form? And how can we explain parallel neighbor filaments, initial elongation of cores, mass-size relation of cores, orientation correlation of magnetic field over very different scales, and magnetic field density relation? And what is the characteristic size of nascent cores? As one of the theoretical predictions we gave, the line shows the analytical result compared with observational data for the radii density relation of infrared dark cloud cores. So if you are interested in these questions and the ultimate question, what does a real elephant look like? Welcome to my poster, and I happily explain the answers we found. Thanks.
Hi. Studying gravitational collapse in massive star-forming core, especially in the early stage of massive star-forming core, is important to understand the star formation process. In order to observe collapsing region, we need to know the adequate infrared tracer. We surveyed 82 high-mass protostellar objects to know which infrared tracer is suitable toward these sources and to find infrared candidates. We observed 4 optically thick molecule lines and 1 optically thin molecule line using single dish telescopes, and we found that toward our source, HCO plus 120 line is most suitable infrared tracer, and we identified 27 infrared candidates toward our source, and we derived infrared velocity using 2-layer model fitting. If you have more interest, please visit my poster. Thank you.
Hello, I'm Nanan. Today I gave a poster about 3-dimensional fitting algorithm of the molecular clouds. We analyze multi-wavelengths of the dust emissions from the clouds and try to obtain the most appropriately solutions of the physicals of the cores, such as the temperature and the density. The method can get the simulate images. We do it by assume a radial symmetric model and parameterize the temperature and the density profiles. We also considered the PSF, the measurement mode, and the noise level, and we try to get the solution by minimization the difference between the simulate and observed images. We have did a lot of numerical tests, and here I just we also did some predict the telescopes observing constraints and distinguish different molecular collapse models. It seems that a reasonable noise level and beam size is needed. If you are interested, you are welcome to talk with me. Thank you.
Hello, my name is Bo from MPE, and my poster is about the disk formation helped by the ampolar diffusion, especially when the small grains are removed. So we know that from Crutcher's survey of nearby dense cores, the cores are relatively strongly magnetized. It's really hard to form a disk inside of these dense cores because you have strong magnetic braking. So we find that ampolar diffusion may be the key to this problem, especially when the small grains are removed. Small grains, I'm saying that tens of angstrom to several hundred angstroms. So because these small grains are dominating these fluid conductivities, and when you remove them, there will be an enhancement on the ampolar diffusion rates. So we can form disks, single disks, or we can form self-gravitating disks. They can fragment. So if you have questions, come to my poster. Thank you.